Morning, good afternoon. What I think you need right now is a little pep talk. So, growth mindset and practice, super important right now. Don't you think? Don't you think? Come on now. Come No, don't shove it aside. Mm-mm. We're talking about practice. Talking about practice. All right. Anyways, okay, back to it. Um, yeah, growth mindset is super important right now because the practice that you do with all this stuff from MyAP, uh, can be super helpful. You can learn so much in application and applying what you've been learning for the last months, and I do think that you can grow a lot out of these. Sometimes that directed test with the explanations that are coming directly from MyAP, you know more than you think you know. You just need to practice. And looking back at the last agenda of what's going on, when the sub was here, there wasn't as many people probably who did the questions online, the review. And those review, I think, are going to be they're going to be so helpful. So today, and as you go through the next couple, we have 11 days, and doing a little bit every day would get you so much farther than saving it to do a huge study session at the end. They're 8-minute videos, they're 10-minute videos. And I really do think that those ones are going to be so helpful in making you understand and helping you understand what's going on with what they want to know directly. And it's going to bleed over. It's going to make the multiple choice questions easier. It's going to make everything easier as you go through. So I really would like to encourage you to do the practice. Don't listen to Allen Iverson. Do the practice, and I think you can grow a lot in the next 11 days. So anyways, let's look at the notes for today, just in case you need an explanation. So we got the first set of notes, which we're talking graphs and proportions, right? And then we got the second set of notes, which is more graphs and proportions, and then we got the third set of notes, which is really the law of conservation of momentum. Just kind of reviews, just trying to like review something each day. And so the first one, the law of proportions, is trying to look at the graphs and saying, okay, how does the equation in the graph relate such that I can get something out of it um, mathematically, and maybe be able to take some shortcuts. And so in the world of AP physics, if you could take those shortcuts, you don't have to do the full equation. That's what they're really trying to get you to do, is take the shortcut and don't do the full equation. And so this is a shortcut, something that's going to make your life easier as you go through. So you look at the equation and you say, okay, this one, for instance, I'm going to go through some of the common equations. So, but they all work the same way. The sum of the forces equals mass times acceleration. And so this is like, there is nothing that is a square. There's nothing that's a fraction. And so this is just a linear representation. So really we just have the greater the force, the greater the acceleration, the greater the force, the greater the acceleration. And you can prove that using the rule of ones. And yes, it does create a nice y equals mx plus b line, linear. But the rule of ones, remember, well, all we need to do is we need to take everything that's not changing and you put a one in it and you compare it, that if you put the other number, if it's times two or times three or times four, most examples on here, I'm going to do times two is the easiest one. So if I take it and I put the rule of ones and everything is one, then 1/1 is one. And if I put the rule of ones and I put a two instead of the one, so the force is double, right? I get with two. So if the force is single, I get the acceleration of one. If the force is double, I get the acceleration of two. And so this is linear, which means if I have twice the force, I have twice the acceleration. And that's what the linear is going to get you every time. Um, okay. And then unless there's a coefficient in front of it. So be careful. There might be a half in front of it or something like that. But this one, energy, we know the E equals mgh, and so this is, once again, it's linear. The E and the mgh, they're the same. They're both on the top of the fraction, and there's no squares. And so twice the height will give you twice the energy. So I have energy versus height, and I have E equals mgh and E equals mg2h, and I get twice the height is twice the energy. Once again, the rule of ones, and you're just substituting everywhere as a one that's not changing. Now we get into one that's a little bit better example because it's not linear. It's actually changing here. And so come over here, and I don't really need you here. So in this case, what we have is we have 1/2 mv squared, which is going to give us a curve. And so the energy is proportional to the square of the velocity. And so as we look at it, we get the energy equation, which is just E equals 1/2 mv squared. If you look at this just so the mass, if we were comparing this one to the mass, it would be proportional. Twice the mass would have twice the energy, but we're not comparing mass in this case. We're comparing energy to velocity in this case, and the velocity is a square on it. So I do the rule of ones and I get 0.5, which just ones in there, and the half has to stay half, of course. I'm just changing, ones for the things that stay one. And then over here, I've got twice the velocity, not twice the mass, twice the velocity. And when you compare 0.5 to 2, it's 4 times as much. And so the energy is proportional to the square of the velocity. And so, like I said, everything that's happening in these pages are trying to get you to think about something that will make your life easier, the relationships rather than the actual direct math for every single scenario. So in this one we have a graphs and proportions. I'm doing a. Can I pause it? I can pause it. Hold on. I'm back. Hopefully it's recording again. So what was I saying? Oh, so this is the next one, and what we got here. So this one, once again, it's got a lot going on in the equation. But we're not comparing every single thing every time, right? This one, we're just looking at the force versus the mass, and so just this force versus this mass, they're both on the top of the fraction, right? And so they're directly proportional, and that would say that the twice the mass would give you twice the force, and that makes a lot of sense. If you were twice as massive, you step on the scale, you'll be twice as heavy, and so that's the force of gravity. And once again, the rule of ones proves this to be true. The only thing I changed was one of the masses. Now, in the same equation, the d is under the fraction, and it's also squared, so the proportion is F is proportional to 1 over d squared, and you get an inverse square as your graph. If you look at the graph, the farther my distance goes, the less the gravity. And the closer the distance goes, the greater the gravity. And it's this shape of the graph because of the square and the inverse. And so if you put the rule of ones in there, if you're twice as far, you get 1 over 2 squared, which is 1 over 4. And so the gravity is split by 1/4. If you give an example, if you were 100 newtons and you went one further radius out from the Earth, you would be 25 newtons of force of gravity pulling you toward the Earth. And the last one of these says, hey, can you do these on your own? Hopefully so. The F and the M, they're directly proportional because they're on the same side of the same top of the fraction. And the F and the V are on the top, but it's going to give you a curve because the velocity is squared. It's not going to be linear. And the F and the R is on the bottom of the fraction, and so it's an inverse, but it's not an inverse square. It's an inverse, but it's not an inverse square. Okay, moving on to the last part of the notes. It's talking about momentum. We've talked about momentum a bit recently, and so this will be just a real quick review. But conservation of momentum says that the momentum at the beginning is going to be the same as the momentum at the end if there's no external forces. So this has no friction on the track. There's no slant to the track. I'm not going to touch it. They hit each other, and the momentum will be conserved even if they hit each other. Now, that doesn't mean kinetic energy will be conserved. So it's elastic if the kinetic energy is the same beginning to end, and it's inelastic if the kinetic energy is not the same beginning to end. Now, if they bounce, they could be either. If they stick, it has to be inelastic. So this one is just basically saying this one's moving, this one's not, and now they're stuck together. So this one's moving, this one's not, and now they're stuck together. We've done that quite a bit. Impulse basically is the idea that says, okay, what's going to happen if we have an outside force? And so the outside force here is probably like me pushing the cart, right? That's me. I'm going to push the cart. I'm an outside force. If I was on a car, like literally, if I was on a cart and I pushed another cart, then I could be part of that two object system. Whereas like this is a two object system, and I could be on that cart. But in this case, I'm touching the earth. I'm on the ground, and I'm just giving a shove, and we're only looking at a one object system here. And so this object is experiencing outside force, and that outside force is going to cause it to change its momentum. So impulse causes it to change momentum. And of course, this could be true in an angular sense as well. And then lastly, we got these two objects moving away from each other. And, if we look at these, it, one of the questions would be like, how is this possible? Like, how could you have the momentum conserved? Well, the momentum is conserved. If you look at it, this one is half the mass but has twice the velocity, and the other one has twice the mass but half the velocity. And so mathematically, it definitely does work. And it also is a good example of the Newton's third law, because the forces between them are the same. So the forces have to be the same. If you're pushing off of something, the force of object one on object two is the same as the force of object two on object one. The forces have to be the same. But if you look at it, it looks like, oh, the forces won't be the same. Well, if they were equal masses, everything would look equal. But the reason it looks different is not because the force is different, but because the masses are different. So the blue one is the twice as heavy, and the green one is the half as heavy. And so there you basically have it. Um, I'd really suggest to take these questions seriously when they do the questions for the practice questions for my AP. And I really do think that the more you practice, the better you'll get, and you'll be able to carry that over to the AP test. I think if you don't do practice, you better be good. That's what I would do. If I was going to try to do well in an exam, and I had questions that were example questions, that would be one of the main things I'd be hitting really hard right now. So have a growth mindset, and don't listen to Allen Iverson. Actually, do some practice, and I think you'll do great. So have a great day, and I hope to see you again soon. Oh, by the way, Wednesday Flex is only for my AP Physics students. So if you want to do um, some questions on Wednesday, it'll right now only have about 15 people signed up. So come on in and ask me questions for AP Physics on Wednesday during Flex. All right, I will see you soon.